Hello everyone, hi, welcome you all on Physics Adhin. In the previous video, we have discussed some important topics and did a revision of a topic that is commutator relationship in detail. So, now I am continuing with finding the average values. So, let us have a first question. Find the average energy provided the wave function is given by this and the energy of being in state phi naught is E naught and being in state phi 1 is E1. So these are the eigenvalues of this Hermitian Hamiltonian or the Hermitian matrix. So that's the Hamiltonian. So first thing you have to check that whether the wave function is normalized or not. So here it is given, but you have to check the normalization. If the wave function is not normalization, if the wave function is not normalized, then you have to normalize the wave function. Normalization. Okay. So here the wave function is normalized because 1 by root 3 square is 1 by 3 plus 2 by 3 is 3 by 3 is 1. Okay. So now find the average energy. So average energy is given. So suppose I'm writing this wave function as C naught phi naught plus C1 phi 1. So here this mod C naught square is finding the probability of that particle whichever we want to detect in phi naught. So energy of phi naught plus probability of finding the state in probability of finding the state in C1 state, in phi 1 state. So its probability is mod C1 square with the energy of that state. So energy is E1. So what is mod C naught square is 1 by root 3 is 1 by 3 E naught plus mod C1 square. So here mod C1 square is I root 2 by 3. So how we find the modulus? So we multiply this, its conjugate multiplied by I root 2 by 3 and then take the square root. So this is mod C. So it's just a complex number. Suppose I have a complex number minus uh, 3i. So how to find the mod minus, okay, let's just take 3i. So how we take the modulus? So suppose this is a. So mod a square is a star a. Okay. So same thing I am doing. So I with minus I will give you minus minus 1. So it will be 1. So this will be 2 by 3 e1. So you say this is 2 e naught. Sorry. E naught plus 2 e1 by 3. E naught plus 2e1 by 3. So this was as simple as that. Now let me have a quick revision on some important topics on this finding average value. Okay, so let me write by point. So expectation value of momentum operator, which is nothing but p cap, which is minus I h cut gradient, which is minus I del. The expectation value of momentum operator this for a real wave function, for a real wave function, this note it down, for a real wave function is always 0, is always 0. So this was the first one. If you have any real wave function and you have to find the momentum average value of the momentum operator, so it's always 0. That was the first point. I will prove this statement when I will be dealing this the concept of this expectation value in during the lectures. Then I will also prove this point. Now, second point is, suppose you have to find the expectation value of an operator which has a eigenvalue lambda. So if this eigenvalue is lambda, then the expectation value of A is simply lambda. And because this is a exact measurement, you have an exact value of eigenvalue. So the uncertainty related with this eigen equation delta A is 0. This was the second point. And the third point, for using the third point, I have solved the previous problem. Suppose the wave function is in norm superposition of many state. Let's say C1 phi 1 plus C2 phi 2 plus and so on plus Cn phi n. Let's suppose it has superposition of n such states, and it has an operator A which is well defined on phi 1, phi 2 and phi n. Then what is the average value of that operator of on this wave function psi? So the average value is defined as, you can write in a simplified form, like the probability distribution mod c I square means c1 square with its eigenvalue, that is lambda I. So the eigenvalue of phi 1 on operator A is lambda 1, eigenvalue of phi 2 with operator A is lambda 2. So this summation from I is equal to 1 to n. So this was the case which I have used for the just previous problem. Now, one thing to remember, that this formula is not always true. This is only applicable for some special operators. So these operators are energy operator, angular momentum square operator, the zth component of the angular momentum, or the spin operator. Spin operator is just basically angular momentum operator. So I'm just writing it here down. So this is the Z component of the spin operator. Remember, these formula are not applicable if you are finding the expectation value of position or momentum. So mod x, sorry, expectation value of x and expectation value of p, the position and the momentum operator. So you cannot use this point number 3 in finding the expectation value of x and p. Okay, so for this problem, I will give you some sample problems also in the uh, fourth or fifth problem set. Already I have provided three problem sets. So give the link will be given on the description box for the drive, or you can just follow the community tab and see previous 5 6 posted. There will be link available. So three or four problems I posted, per PDF. I posted three or four problems. So you can just have a look on it. Uh, Look, those are the concepts which I am teaching here. So better is if you can solve those problems and study this revision tool. Okay, now the next important topics is particle in a box, and the question is, find the energy of the given wave function, and your given wave function is psi. Let's say at x and time t is equal to 0, the wave function is given as a sine, let's suppose 2 pi x into cos pi x, and the part and the potential is over the range 0 comma 1. So from here you can just quickly draw this diagram, that this is the situation, this is the infinity potential, and this is the 0. So the potential is not symmetric with respect to origin. If the potential is not symmetric, then this wave function will have indefinite parity, means not defined parity. uh, I don't know, you did you have a concept of parity or not? So let's leave out parity. So just decouple this wave function. So if you decouple it, so what you should do, just multiply it by 2 and divide by 2. So you will get 2 sine 2 pi x into cos x. So this you can write as a sine a plus b. So this is 3 pi x, and sine a minus b. So this is sine pi x. Now you compare this wave function with the standard wave function. This is under root 2 by L sine n pi x by L, where n is a quantum number. Okay, so this was 3 pi x. So 3 pi x corresponds to n is equal to 3, and this 1 corresponds to n is equal to 1. So 1 is your ground state. So this is your ground state wave function. N is equal to second excited state. So this is your first second excited state. Okay, so this wave function, the given wave function, was a superposition of ground state and second excited state. Now there is a constant a. So what you should do here is root 2 by L. So you just first of all you have to normalize this wave function. So what you can do is a by 2, just multiply it because the length is 1, so we don't have to worry about this L. So this will be root 2 times sine 3 pi x plus root 2 times sine pi x. So for our convenience, we can write this wave function as phi naught because this is a ground wave function, this wave function as phi, let's say second excited state, so we can write it as phi 3, sorry, phi 2, not phi 3. So phi naught, phi 1, phi 2, yeah. So now you have an idea about how to normalize it wave function, just mod psi square. So this will be 1, this will be 1. So you can calculate the value of a. So your a will be coming out to be 2. If you just calculate it, I have calculated in my rough sheet. So it will be 1 by root 2 phi 3 plus 1 by root 2 phi 1. So it has an equal probability. Now using the previous concept, find the average energy. Average energy, so the energy of this particle in a box is n square pi square h cut square by 2m. This is basically the length square. Okay, here the length is 1, so I will put as 1. So suppose the this well was from -1 to 1, so this will be 2 square because the total width of the well is 2. Okay, so average energy of the second excited state, n is equal to, sorry, again I have written it's 3, so write this, right, this is phi 0 and phi 2. So for second excited state, n is equal to 1 2 3. So this is ground first second, so second excited state n is equal to 3. So 3 square pi square h cut square by 2m multiplied by probability chi square plus the energy of the ground state is pi square h cut square by 2m with its probability. Just calculate it, whatever is, this is the answer. So this was just a normal procedure for which you should follow to finding the uh, average energy of any. So this was just to calculate the average energy of the particle in a box when it is in superposition state. Now let me give you some insights, some topics on this particle in a box. So just you have a quick whatever you have studied. So if the width is 0 to a, let's say this is the width, then the wave function is given by 2 by L sine n pi x by L, where n varies from 0, 1, 2, sorry, not sorry, not 0. 0 is not a defined quantum number. I'm very sorry, not 0. This is starts from 1, 2, 3, 4, and so on. 1 corresponds to ground state, second corresponds to first excited state, 3 corresponds to second excited state, and so on. And the energy of the wave function is given by n square pi square h cut square by 2ml square. So this was the first point. Now if you are on the symmetric potential well, let's say 0 a by 2 to a by 2, means the center is at symmetric, then it has a definite parity. Definite parity means one time the wave function, it has a defined parity. So the wave function is, I'm writing the both. So 2 by L sine n pi x by L is the wave function for, okay, let me write the both and then I will tell you which is for what. So this is sine 2 by L sine, let's write by m pi x by L, where m is equal to 1, 3, and 5 and 7. So this is the ground state, second excited state, fourth excited state, sixth excited state, and so on. Sorry, I again made a little mistake. I'm very sorry. This is not sine. This will be cos. Cos m pi x by L. So, and here the n is 2, 4, 6, 8. So 2 corresponds to first excited state, fourth corresponds to third excited state. So all the odd excited states will have sine wave function and all the even excited state including the ground state have the cos wave function, okay, if the potential is symmetric, and energy remains the same, n square pi square h squared square by 2m, the length square, here the length was 0 to a or 0 to, let's call it as L, I have written at L. So uh, rewrite this as minus L by 2 to plus L by 2 because I am using here L. So this was the first thing. Now the question that has been asked many times in these types of examination is this. So suppose you are in a symmetric wave function. Okay, whether it will be from 0 to a or it will be from minus a by 2 to a by 2, this doesn't matter. So if, let's suppose it is from 0 to a, because this will give you a clear picture to study this. So let's suppose this is from 0 to a. Now I have an ask, what is the probability of finding the particle from 0 to a by 2? Means this. So what is the probability of finding this? So from pictorially we can see that this is the half of this value. Okay. So the answer will be 50%, or the probability of finding the particle is half from 0 to, if I am asking from 0 to a by 2. Now if I am asking what is the probability from let's say a by 4 to uh, a by 4 to a by 4 to 3a by 4, means I am asking the following question, that this was my 0, this was my a, so this is my a by 2, and this is, sorry, a by 4, and this is my 3a by 4. So what is the probability of finding the particle here, like in this region? So you can, so for this you have to exactly calculate, but the option intuitively you can guess that this is greater than half, because the area covered by this region is more than half. So this was the first thing for ground state. So this was for ground state. Now let's consider for first excited state. So this is your first excited state. Okay. So again the same question for this. What is the probability of finding the particle from 0 to a by 2? So we draw a line on a by 2. We see that this distribution and this distribution is all equal. So this probability of finding the particle from 0 to a by 2 will be half. Again the same question from minus a by 4 to plus a by 4, minus a by 4 to, sorry, not minus, it's a by 4 to 3a by 4. So probability of finding this, so we can see this is this area is equal to this area, and the distribution here will be symmetric, so this area will be nothing, will be also half. So for ground state, the probability of finding the particle between the range a by 4 to 3a by 4 is greater than half, but for the first excited state it is equal to half. So these types of questions can be asked, so you can uh, answer them pictorially, provided you have to very careful about what for which range that question has been asked. Like I have given you two options, 0 to a by 2 or a by 4 to 3a by 4. This can be asked for this can be further reduced, and it can be asked for higher excited state, for ground state, or for so I have told for ground state and first state excited state, but this problem can be generalized to any excited state. So by seeing the pattern like ground state and first excited, then you should try for second excited and third excited. Then you will know what type of probability will be on even like zero, ground state, second excited, fourth excited, and what kind of probability will be on first and third and fifth and so on. So this type of question can be asked. So make sure you just have you just know how to solve this type of problem, and you can find this type of problem in any coaching material or any examinations. Definitely you will get there. Okay, in the next video, I will be dealing with two more potentials, that is a finite potential well and the harmonic oscillator. So in the next video, I will be dealing those two, and the further next video, I will be dealing hydrogen atom, because Many simple questions are asked in jam exam, or some advanced questions is asked in just exam. So I will be covering that topic in very brief, or it may be possible I will be taking all the three topics in the next video. So okay, that's it. But this problem, the infinite potential well, this is one of the most important topic and most asked problems in jam examination. So make sure that you study this topic very well. Okay, that's it. Look, this topic is very simple, but the questions has been asked in 1 or 2 marks question. See, the idea is the question of the examine sorry the question that has been asked in jam exam are not too difficult, are very simple formula based, but the only concern is about the time, that you have a very less time and you have to solve more problems. So make sure whatever questions I am giving, you don't feel that you don't know or you don't revise the formula. So I am just here to giving you a quick revision of these formulas. So make sure you revise all these formulas, like the wave function, the energy eigenvalue, how the wave function changes when I have a symmetric potential well, how the probability distribution function look like, so ground state and first excited states. So these are the basic key points of this potential. So you should always remember this so that you can give more time to other problems. So that's why this revision process is very important. So make sure you, okay, I will be discussing this topic in a separate video. Okay, see you in next video.